All right.
Okay. Okay. So, yeah, I'm now walking at Okinawa, South Island in Japan. So that's really, this is the Okinawa Institute of Science Technology, relatively new graduate school. And my house is around here, actually, and inside the campus. And yeah, this is the view from my house. So I assume that your place should be a lot of snow, but our place have no snow at all. So big difference, I think. Anyway, so today I'd like to talk about exploring robotic minds using the free energy principle. Okay, so and my talk today will be like first I provide you the brief overview on predicting the active inference. Okay, and our past studies, and then go to the introduction of something called PVRNN as a free energy based recurrent neural network model. And then after going through the basic of this model, I'm going to introduce some robotics experiment using this model. And that include social interaction, imitative interaction, that's the robot-robot interaction or human-robot interaction. And then go to the dynamic goal-directed planning based on active inference. And then I show you some summary. So that is my plan today. And hopefully finish 45 minutes or something like that. Okay, so then I like to provide you a brief review, the predicting active inference, but probably the many of audience there might know the free energy things, and but I provide you just briefly the brief introduction of this concept. So, and predict coding is a theory for the perception. So that is, yeah, and that is uh, that is idea is try to minimizing the error between a top-down sensory prediction and its bottom-up outcome by the inferring the latent state. So it's based on using something generative mode and predicting, and then so it goes based on the prediction and the outcome. So reality comes, and then if there is an error, and the error has to minimize by updating latent state. If you can infer the latent state, the perception achieved. That is the idea. And active inference is a theory for the action generation. The idea is that minimizing prediction error by changing sensory inputs by adequately acting on the environment. So therefore, this is, of course, action-centered. So prediction is minimizing by inferring the good way to act. So through the action, sensation change, and then prediction error is minimized. So, and the important thing is that these two are not separated process, as action and perception make a loop through the environment. So, okay. So, and then my group have worked on the concept analogous to predicting active inference. I think I would say more than 25 years. Then I like to briefly introduce the idea. So that is I used to work on continuous time recurrent neural network, but hierarchically organized recurrent neural network. And then this recurrent neural network is like a higher layer is slowly operated. That is a time constant here is large. So then, and this is a first layer. So then that one is time constant much small. That's why fastly changing. So that's kind of a connection we consider, connectivity consider. Then uh, then this is maybe kind of prefrontal or associative layer, and this is going to be the peripheral. For example, this might be the proprioception or in case of a robot, it might be joint angle things, and this is might be some kind of visions. So then we consider like we have an intention for acting for the environment, then starting from the this highest layer, and then that is provide kind of anticipation about sensation, both for the vision and the perception. And for example, it's like what kind of a joint angle change or perception change or what kind of visual image can be seen when acting on the environment or specific on acting environment on some specific intention. So this is top-down intention and associated with kind of prediction. So the predicting perception, that joint angle, that one is fed into the some controller, like a PID controller as a target. And then, now, it generates, converts the motor torque and acting on the environment. And then actually you get the actual sensation of perception and the vision things. And then you got the error. And the error is in the bottom up. So by carrying error signal as bottom up, and then it's going to have a top-down, bottom-up interaction, and then resultant, we might have some kind of conflict that what's saying about top-down and bottom-up conflicts. So then idea is that we want to minimize these error is kind of an outer error and internal error or conflict. All these things have to be minimized. The one by updating this intention of the all layer. The other is generating action and changing the environment. So therefore, that is a central idea. And then therefore, in the one side, the mind state is changed. That is the intention updated. The other side, the world state is changed by acting on the environment. How these two extreme things, two sides of poles, are changed depending on the dense interaction between top-down, bottom-up. So then we want to clarify the mechanisms by analyzing phenomena, by conducting robotic experiments, synthetic neural experiments to generate this dense interaction between top-down, bottom-up, and then they look at the phenomena. So that is what we are doing. So, and then yeah, as a chairman introduced that, so I wrote a book about this. Okay, so however, one thing is that I have worked a long time on deterministic dynamic recurrent neural network. So recurrent neural network is basically deterministic, like LSTM and those things. So then the problem is that there is no probabilistic treatment. So, and then, yeah, but deterministic dynamics people say that is a probabilistic phenomena can be well imitated by developing deterministic chaos. So that is the one that is including me. We used to say that. So, but the formal probabilistic modeling people say that yeah, we better to use formal model like a hidden Markov model or something like that. And then those two camps of people didn't discuss so well. So then, and are there any ways to bridge the gap between these two way of thinking, so deterministic modeling and based on the chaotic dynamic things, and the other is stochastic dynamics or probabilistic dynamics? Then I thought that, yeah, like I think I was invited to Carl Friston to give a talk in his laboratory, like 2009 or something like that. Then I first time learned about Bayesian things. So before that, I was deterministic, completely deterministic modeling person. I was not so familiar about that. Then when I got to learn from him, so then I thought that yeah, it's kind of Bayesian approach, and we can make a continuous path from deterministic modeling to the uh, probabilistic model. So that I thought. So then if we can do that, so that we can look at something called phenomenological origin of probability. So it's what is the origin of probability? So that is one thing I'm interested in beyond the robotic study, but also it's quite related to the robotic studies because robot thing is kind of in a working in a noisy environment. So, but is the thing is something like that. If there are noise, is that really probabilistic one or maybe deterministic? But that is very difficult to identify. So, but anyway, so then under such motivation, so we developed something called PVRNN, so that a variation recurrent neural network model using free energy principle. So then I like to introduce first this model. So so PVRN, that's called predicting coding inspired variation based recurrent network. So so that is the idea is that yeah, like a conventional free energy minimization, we want to maximize the accuracy terms, the maximizing yeah accuracy term, and then minimize the complexity term. Then that is it's usually more difficult for complexity term, but in this case is that this is the approximate posterior and the prior K divergence between approximate posterior and prior. But what is that prior posterior is that in a more intuitive way, the prior is a top-down pathway. It's a top-down one, the prior, and the posterior is bottom-up one. So then we want to minimize conflict between these two. Then this accuracy term is the outer error part. We want to minimize both of them. But my case is that our case is we put some kind of parameter we call meta prior W, and then regularization for the complexity term is weighted by this meta prior W. I'm going to explain this one so later more. Okay, so then I'm going to explain the graphical model of this one. And so this is time step goes this way. So then we have a first probabilistic latent variable. So, and then that's with Gaussian distribution. And then that part is something we are following the idea of sequence Gaussian prior proposed by the Chung. So we have a prior and actually and the posterior at each time step. So as a latent variable. And then okay, so then this posterior things is mapped to the another latent variable. That this is deterministic latent variable. So then this one, so for example, D step one is going to predicting the next step prior. So okay, so the D2 is going to be the prior predicting prior of this one, step 3. So, and this deterministic latent variable is further mapped to the prediction of sensation like proprioception and vision things. And then we have an observation. So of actual observation here. Then what we want to do in case of the learning is, so we have a kind of so this is try to deconstruct this observation by prediction or deconstruction, but there should be some error. And the error is going to be minimal. Error is backpropagated. So backpropagate through time and backpropagate. And it's going to the also posterior part of this one. That we want to update posterior using this error signal each time step, and also wants to minimize scale divergence between these two, then updating. So that is actually what we do is something like minimizing the error part or negative log likelihood, and also the minimizing complexity term. So that is scale divergence between these in prior and posterior. So we have to minimize both of them. So then if we can minimize, then what we get is nice synaptic weights as well as posterior distribution along the sequence. Okay. So, and we're gonna look at and then next I'm gonna show some simulation, but we look at the effect of this metaplier W. And the first in the learning in the simulation, also in the robot experiments, we look at this effect during environmental interaction by the robot. So that will be examined. So very much focus on this something called metaplier. Yeah, this parameter is very important in today's my talk. Okay, so. And the simple experiment we have done is something like this. So this is a probabilistic finite state machine, like 1, 0. Then after that is going to be 1 is 70%, 0 is 30%. And then we consider this kind of probabilistic finite state machine and generating training sequence, like a 1, 0, then this case 1, 1, 0, this case 0. So this part is and whether 1 or 0. So it's question 1, right? So then we make a long sequence of this one, and let's the one layered PVRN to learn it. So it's a learning experiment. But in this training simulation, we change the metaplier as a large one and small one and compare the learning results. Okay. So that is the test generation after training with different value of the W. So that is so this is a case of the relatively large W 0.1 compared to the small W 0.025. And then first we look at this large case. This is the output generated after the learning, and 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1. So anyway, this is following mostly this progress finite state machine. So the output is almost okay. So, and then when we look at the prior sigma, so prior, and then, so that is prior, I mean, that is this one. So this one is Gaussian distribution. So, and the sigma, Gaussian distribution parameterized by the sigma, that I'm showing that sigma. So then it looks like almost 0, right? So, and then that means that there is almost no noise added. So there is no probabilistic component, but still this one is generating probabilistically by following this one. So then what we found is that the deterministic dynamics is developed when the W set larger like this value. So, but on the other hand, if you set W is relatively small compared to this one, then again, output is following this one. So, but the representation of a random latent variable is different. In this case, prior sigma is whenever here, so here is a gray bar part is kind of a this is a question state. So 1 or 0, we don't know. So then in the precision is a sigma goes up here. So this is low, during 1, 0 because this is deterministic, but this branching point, it becomes high. So that is in this case, stochastic dynamics is generated, the adapting the prior structure, precision structure. So every third one, sigma becomes larger. That's why here is branching. So, but in this case is that based on deterministic chaos and probabilistic, seemingly probabilistic phenomena sequence generate. So that is the difference. So that's kind of difference comes from the different setting of the metaprior value. So the weighting of the complexity term. So, so then what we can see is that so when we observe the fluctuated seemingly probabilistic sequence, but you can reconstruct them different way by changing the W. So metaprior W, if it's set larger, then it's going to be the high precision prior, small sigma is generated, and then it's going to be the deterministic. On the other hand, W set very smaller, low precision prior, so it's a large sigma, then it's the process is the probabilistic random process is generated. So that's a different way of representing this one is going to be fractured temporal, observed temporal pattern is differently represented, depends on the W. So now, so I like to go to the embodied cognition. So that is which aspects in a human's embodied cognition can be accounted by this W-dependent structural development shown in the PVRNN. So in order to address this question, and yeah, my students, uh, Nadine worked on a robot-robot imitative interaction. So initially, we didn't work on this, we didn't look at this question directly, but after doing the experiments, we found some kind of the answer for this question. So, but anyway, so I like to introduce now for 10 minutes, what she did during her PhD study. So what she did is something called synchronized imitative interaction between the two robots implemented with the PVRNN. And then in this setting, so that each robot is pre-trained to generate or predict sequence of primitive movement pattern that follow a specific probabilistic finite state machine. So like this one. So this is robot one, robot two. The training for each robot is done independently, not through the interaction. So it's kind of supervised training we did. So then robot one is trained to generate the movement pattern A, so like this one. Then followed by 80% movement pattern C, and 20% by movement pattern B, like this one. Okay, so then coming back to here, and repeating A, and then again 80% is C and 20% B. So, and then in the learning of these patterns, robot learn about on joint angle sequence, proprioception sequence. Also, it's like on mirror image, how it looks like visually, like my two hand moving, how it looks like my hand moving. So that is associating proprioception and visual sensation things, the sequential proprioception and the visual sensation. So they learn to regenerate visual proprioceptive sequence. So, and the other robot 2 is going to learn, and after generate pattern A, this case is 20% C and 80% B. This part is conflictive. So conflictive means that when these two robots, after the learning, have to imitate each other synchronously, while doing A is fine. But after that, this robot wants to do the 80% C, this robot wants to do the 80% B, then imitative interaction becomes difficult. But we intentionally set the system in this way. So setting this way to look at conflictive situation. So and the training is repeated with setting different W value for each robot. So that is yeah, two robot different W in we did a different combination. So then, and after learning, two robots interact by generating on intended movement pattern while perceiving pattern generated by the other. So that is a movement pattern generation is done by coupling two robots in following in this manner. So this is robot one, robot two. The robot one generating in a own movement pattern and based on the prior and then both prediction of and proprioception vision is generated. So and the prediction of joint angle is fed into the controller and actual movement is generated. And the actual movement generated, and then the other robot can see it and predict it. Okay. So the other robot also do the prior generate and prior, and then we're going to predict vision and all movements, predict all movement. So then, so this robot is predicting this robot, robot two, and actually can see the visual image. And if the prediction goes wrong, the error generated. Error is bottom up, and then posterior is updated for minimizing free energy. In the same way here, so we're gonna do the error generated here, and the posterior is updated, approximate posterior is updated. So in this manner, two robots are coupled. So uh, through the error signal actually. So then this time we did experiment use three levels of PVRNN. The higher level is slow dynamics and the lower level fast dynamics. So and then this is something like it's a time step, and this is a past and this is future prediction. And then what the network does is that it's going to top down from the higher to lower, and the time from the forward time steps. So the signal goes this way, and finally generating visual perceptive prediction or reconstruction. So because this is the past part, already it is an observation is made, and the network try to reconstruct this one, nicely reconstructing this part by using the error signal, and then using error signal and updating the posterior with each time step, each layer by minimizing free energy, right? And then after nicely minimizing free energy, then network can predict next steps. That is minimizing free energy here is required in order to make the latent variable situated to the past sensory observation. So the once it's situated, then prediction can be made very nicely. So therefore each sensory motor step and we do kind of like 100 epochs of the iterative computation minimizing free energy. Then after that, we're gonna do the one step ahead. So like a 100 millisec sensory motor step, we have to do the 100 iteration of backprop things, for minimizing free energy. So that's require a lot of computation. So okay, so. And then specific question on this experiment is that what sort of interaction can emerge? Do they always imitate each other synchronously, or do they sometimes generate their own intended movement by ignoring others? how does W, multiplier W, affects the nature of dyadic interaction? So let's look at the robotic simulation, robot experiments for this one. So, okay, so then the first is that so this is the first setting is that this robot sets the multiplier W very small. This is large, and these two robots interact. So okay, so now what you see is that the left side is low W, the high W. Then you see that okay, so then this is kind of a time step. The now is here. Now is here. This is a past window, and this is a future. So then what you see that low W, robot one is very fluctuated, but this one is with high W, very stable predicting. So now they are doing try synchronize A. A is fine, but after that he's generating B, and this is delayed by the following B. So this okay. So now doing the A, and then this robot is preferred pattern the B generated, but this robot is unpreferred pattern generated. So that is okay. So this side of the robot prefer to generate C, but it's generating B by following this robot 2 with high W, set with high W. So therefore, what we see is that this is becoming a leader. This is, robot is a follower. So that's kind of situation we see. So next is that we set both W high. Right? So then first you see that the both is very future prediction, very stable. So then you look at this guy is generating C, this robot is generating B. So now it's generating both A, and then after that, this robot generates the C stably, this robot generates B. So that the own preferred pattern generated, the ignoring each other. That is the case when the both robots set with high W. Finally, what we did is kind of in both robots set with small w. First, you see that very much unstable future prediction both sides. So because of the w is very small, now what we see is that now doing A, so then it's kind of happen to synchronize with C, but unstable manner. So in this situation, in this setting, sometimes we see some kind of turn taking between the full leading and following. So it's kind of under very stochastic situations, we see kind of random switch like things. We often see those phenomena. So, okay, so now I like to show the case, some, how internal representation is developed. This is a case that the robot 1 set with small w, robot 2 set with large w. And what we see, this robot 1, both robot is kind of synchronized well, C, A, B, A. So but the important thing is that this I'm showing this one is a lower level random latent variable, and then this green one is prior, and black one is posterior. Then you see some kind of gap or small gap, but there is gap. In case of W set very small, so that is a W set small, so therefore KL divergence is allowed to grow larger. That's why you see some kind of gap between the posterior and prior and posterior. But on the other hand, if we set W is larger, then more constraint for the complexity term. So therefore, there is less gap between. Okay, so that is we see it. And also maybe time scale difference we see. This is highest layer random and random latent variable is much more slowly changing. Actually, when it comes to the A, it goes up. When A goes up. So that is kind of encoding's primitive sequence. But this one is a inside primitive primitive pattern is encoded. So that's different we see. So both cases. Okay, so then something what we can say is that this robot is set larger W. This robot is set with small W. Then what we see is something like uh when set with larger W, so prior becomes more precision. So very small sigma, high precision. That's why uh, and posterior is attracted to the prior. So therefore, that's why this robot with high W's tends to generate unintended behavior, ignoring sensation. On the other hand, when we set W small, the prior is a low precision, so large sigma. So that's why posterior is attracted to the sensation. So that's why this robot is more sensory oriented, or maybe affordance like a robot, less on intention, but very much depends on the own behavior, depends very much on the own sensation. So like that kind of behavior generated. So that's, you see here we see the leader follower relationship is developed depending on setting of multiplier W. Okay, and then next is that shifting W, multiply W during the interaction. So that is in our study, W was a set in the training phase. So then once the robot trained with high W or low W, and high W is more intended robot generated, but a small W robot trained to be the more or less positive robot, sensory driven robot generated. But however, question is, can we arbitrate top-down, bottom-up process of an agent by shifting W during the interaction? So once trained some specific W, but we want to change characteristic of the robot or agent by shifting W during the interaction phases. So can the same individual becomes active or passive by changing W depending on the situation? And my student Wataru showed that yes, we can. And then another student, Hiroki, he followed this idea and do the experiment in human-robot interaction. So, and what he did is that the robot is trained to generate movement pattern transition by following this probabilistic finite state machine. So this is something like showing that movement pattern A generated, and after that, the B pattern or C pattern generated, and something like this one. Then what he did is that after training the robot, and the robot is generating movement pattern probabilistic transition by following these things, and then Hiroki is induce robots to induce a robot for the untrained transition, like generating this one to C, like this one, right? Then he examined what kind of reaction force comes back from the robot, depending on setting of the W during the interaction. So, okay, so then this is something like an experiment he did. This is after the training. Oh, sorry. So now robot is generating a pattern, and then so this scale divergence and force things, and now he forced to something new pattern, and the error force generate error. Okay, it's not so clear. I'm sorry. So when he starts to interact, and the first force goes up, reaction force goes up, and the KLD divergence becomes larger. So then now you see the pattern switch. So you see this pattern to the now switch to the another pattern. So that kind of things now he experimented. So then what do we okay, so and what he observed is that when the setting W large, it's very hard to change tolerable movement, robot movement pattern, encountering with large reaction force with its strong intention. So, but on the other hand, when set with small w, it's very easy to change the movement patterns, encountering only with small reaction force from the robot with its weak intention. So that is we see the difference. So it's kind of excess torque. W is larger, much larger. So reaction force becomes larger. Difficult to more force required for the human to induce untrained pattern, untrained transition. So then that is something like and the human can feel the intention of the robot through the kinesthesis, so through the force. So that the idea is that the top-down prior or intention robot can be translated to the reaction force. The human can feel intention of the robot through the force. So that's kind of a force level interaction, and it could be very important between human and robot. So that is one thing we did for human robot interaction experiments. Okay, so then what we have seen so far is that arbitrating between top-down intention and bottom-up perception depending on the W. So that is when we set larger W, large W, and then the high precision prior comes and the low precision. So therefore, it's more strong top-down, and then it's going to induce, rather than changing on mind, but the environmental part is going to be changed. So on the other hand, so that is a kind of, in this case, subjective mind extended into the external environment. So on the other hand, we set smaller W, then we're going to have a low precision prior. So then, therefore, we're going to have a more stronger bottom up, and it's going to change the mind rather than change the environment. So, okay. So in this case, the external environment extends into subjective mind driven by sensory affordance. So the question is that can W adapt autonomously? So that is the idea is like adapting W depending on the level of uncertainty in the world. So this is not yet we have done, but we are thinking now. So that is, when the world looks more certain with less dynamic change, then W should adapt to much larger W. So that is because prediction doesn't goes very well. So then we can rely on a strong top-down prediction. So, but on the other hand, when the world looks less certain with more dynamic change, we should not rely on prediction, own model. So rather than more following the sensation, so they're allowing more strong bottom up by adapting W to the small. So we are now working on how to adapt W autonomously. So that is, yeah, current ongoing study. So I think I already talked about 45 minutes, and then also I have one more topics about goal and dynamic online goal like planning things, but I think probably I cannot have time to do this. So then yeah, I go to the yeah. Yeah, but maybe something I want to do, yeah, show you just some so what we do is something like online goal direct planning and replanning. So that is like so now this is a goal position, and this object located random place here. Then robots makes a plan how to moving this one to the specified goal. So the robot actually doing that through the online error regression for the past. So that is minimizing evidence-free energy for the past. The simultaneously expected free energy is minimized for the future. That expected free energy minimization is action planning. And minimizing evidence-free energy part is perception. So the while perceiving how the world is changing and future plan generated. So therefore, we can do in this framework, we can do the dynamically regenerate the future plan based on the current perception. So maybe something like this is that, and so in this is original goal action planning, but now if human interfere, so that is the robot is going to be specified goal somewhere, and he is now moving toward that one, but the experimenter interfere and the object dropped, and the robot is going to but cannot do so much because he doesn't know how to recover this one. So, okay, so then human assist robots to complete task. Then the human is going to, uh, okay, again, interfere first, human interfere, then robot is lost, and then the human assist robots to complete the task. That is kind of a incremental tutoring. So now he's teaching by feeding the robot force and teaching it how to do it. And then robot repeat, and we repeat these things in several object location point for generalization, and repeating several times, and then in the end, uh, what we got is something like okay, so this is after two rounds of increment line. Okay, so then interfere once robot is lost, but the robot can now self-recover it. It is kind of slow, but he can do it. So, oh, okay, so this is a little bit rush up. So today I just summarize. Yeah, today I just I showed the proposal of PBRN, and I showed some kind of a numerical characteristic like arbitrating the top-down bottom-up strengths by changing the W, and how the W can adapt automatically as a future. Uh, okay, so I'm sorry, this is something wrong. Yeah, this one. So summary is that it has an introduction PVR model based on free energy principle. I show you kind of deterministic versus probabilistic uh, depending on metaprior setting W. And the robotic imitative interactive interaction experiment was shown. And we show kind of leader-follower relationship and it's and the precision structure. So, and the top-down prior can be translated, and also I show that the top-down prior can be translated into the reaction force. Finally, I show briefly about online board planning, dynamically planning, and incremental learning. Finally, I would like to say that why I like to say why is FEP is important. In my thinking that this is important because it provides a second order representation in terms of precision. So all these deterministic recurrent networks only first order predicting itself. But now, precision, or precision of belief, how much my predicting value is correct, certain. So that's kind of second order representation comes. That makes the things much more richer and very useful, especially for the robot working in a noisy environment. So that's all the things today. Thank you very much.
Well, thank you, Dr. Tani. So how much time do we have for questions? 8 minutes? All right, so we have a few minutes for questions. So I'm going to take some from the audience and then you can
Yes, please.
yeah, I'll repeat them back. So Rodney?
Yeah, so my question, as we saw some of the free energy demonstrations, we saw that this method can replicate patterns once it's shown to the robot. And one of the things that I'm interested in is if this method has been used, or if he knows of a way that this could be used to mimic the transition function from like old school Q learning method. Because right now, deep Q learning doesn't do the transition function itself in the optimization process.
Were you able to hear that, Dr. Tani?
No, I cannot hear at all.
Yeah, Rodney, can you come up? I think it's better instead of me trying to repeat it because your question's a little nuanced. Maybe come up and just say it directly to him.
Well, so a little bit of my work is in reinforcement learning. And one of the things that was interesting, that stuck out to me as I saw your work, is that robots were able to replicate patterns that they were showed in different orders. And part of that that interests me is the transition function in old school Q learning methods. Part of that has been lost when we use deep learning networks. I was wondering if you've seen any way to replicate like a complex state to state prime transitions with the priors. So instead of just like pattern 1 to pattern 2, go from one pattern to another pattern. So from pattern A to pattern C, from pattern B to pattern A, in different order based on different priors. And I'm sorry if I butchered some of your work. I'm not an expert in it. I'm just trying to get an understanding of how I can use some.
But your question is that not just from one pattern to the another, but more including hidden state like things. Are you asking? Yeah. I think actually we okay. So previous okay. So that is where is it? So I'm gonna okay. The example I use, this one is already, I think, hidden state. It's because it cannot determine just by observing which pattern now. Is you need the history of the past sequence in order to identify the latent variable. And also, today we couldn't show that any reinforcement learning related combined with active inference, but we are working in a, because maybe you know Kenji Doya, I work together with Kenji Doya, and who is very good at reinforcement learning. We are working on a lot of a hidden state program. Yes, yeah, but that is, if we use deep learning like a recurrent network, it's well known that the recurrent network can extract hidden state representation very nice, not always nicely, but at least it can do some level. So
Thank you.
okay.
We still have some time. Any other questions? I'm sure that there's more. Oh yeah, Cece, yeah, just come up here and ask.
Thank you so much for the talk. It was really great. It gave lots of ideas. I have lots of questions, but I'm gonna just stick to something very brief.
Yeah.
You also mentioned that you had a pre-training piece of this. How important is that pre-training piece for these behaviors that, you know, emerge?
So you mean it's a pre-training? Yeah. But okay, today what I talked about completely based on supervised learning things. So it's really pre-trained because as I told you, my group is also working on the simulation, but no, reinforcement learning exploration based, but that was totally simulation. So because it requires always 100,000 trials, something like that, that we cannot allow robot to do the 100,000 trial. So therefore, we have to do kind of a tutoring the robot, but these days by kind of incremental tutoring. So without that is current this kind of hardware robot cannot be trained. If we allow them to self-explore, it takes a huge time. So then it cannot converge. Do I answer the well?
Was that what you wanted, Cece?
Yeah, I mean, I guess I was wondering how it formed part of the framework, since it is important, which one would expect, like you said. And as the robots are accommodating, like how important is that piece for their accommodation to each other? So if you have a language interaction, for example, there will be accommodation to the kind of speaker. If somebody's speaking to a child, the
Of course.
dialogue will
Yes.
be different.
Yeah.
And that's actually also multimodal.
Mhm.
So,
Yeah.
so I was kind of thinking, you know, in terms of you know, the parameters that they are exploring, the pre-training seems to be an important one to also consider, you know, in that process. But yeah, I think you answered it.
Yeah, thank you. Yeah, but we have to work on that aspect.
Oh, of course, there's always more. We also have a
Yeah.
question online.
Yes.
Do you want to take it?
Yeah, the name is Mehran. I was told to put the affiliation there.
Please speak up a little
Yeah,
bit
can you speak up?
larger.
Your volume is really low.
Can you not hear me now? Is it better?
Yeah, I can hear. Yes,
That's
I can
better.
hear.
Speak like
Thank
that.
you.
Okay, so apologies for that. It's supposed to work better. Just once. Better now, right?
Yeah.
Yeah.
Perfect, perfect. I appreciate the talk. That was absolutely amazing, Professor. Thank you so much. I just have one particular question about the formulation of the state space model under the predictive coding part of your project. First of all, what kind of state space model are we looking at? Is this sort of a continuous time, continuous state type of state space model?
Yes, it's actually wants to do the continuous time, continuous space, because it's based on continuous time recurrent neural network model, like ZIPSA all the day develops. That is, yeah. So therefore, yes.
Okay.
That's why so we have a time constants tau in.
I see. All right.
Yeah.
So
Yeah.
if that's the case, because this is a highly dynamic environment, I wonder if you ever use the generalized filtering or generalized coordinates of motion.
Generalized what? Filtering?
The generalized coordinates of motion or generalized filtering, basically. So basically having more than just the velocity of the hidden state modeled as a differential equation, but also having, say, the acceleration, the jerk,
Okay.
and higher, because
Yeah.
because
So
in this context you are dealing with like while you're minimizing the free energy,
yeah.
you're sort of tracking a moving target. So by the time you've minimized it, it has already moved.
Yeah. I think is that the original paper by the Freestone is in that way. So, but I thought that it may not be so necessary if you generate movement in this level. I mean, my robot movement not so how to say, precise, or so if we ask the robot to do more complicated, skillful behavior, we might need more higher order things like acceleration, those things. But up to now, current task is, just this one is enough. So the second order, yeah, no, first order, just dot is, yeah, one dot, yeah.
Thank you, Professor. Thank you.
Yeah, thank you. Yeah, generalized coordinates of motion are an interesting thing to look at with respect to the free energy principle. Well, anyway, thank you very much, Dr. Tani, and thank you everyone for the good questions. I will just
Thank you.
remind, I will just remind you that you'll get to interact with Dr. Tani tomorrow as well at breakfast. And so we can please bring in lots of good questions and comments, because this is very exciting work, and I think those working in the free energy principle, have a lot to offer to not only just robotics, but other domains in artificial intelligence too. So again, let's give a hand to our speaker one more time.
Yeah, thank you very much. Yes.
Thank you very much, Dr. Tani. It was great.
Okay, good night to you.
Yeah, good night. Yes, bye-bye.